want you guys to look at my eyeball for a second here. Could you see it dilate? Hopefully you can see it dilate. So a dilating eyeball is when it gets bigger, but then it contracts too. So getting bigger and smaller, that's what a dilation is. It's the same way in geometry. Dilations are when we get bigger or smaller by some kind of scale factor. So one of the things they want to point out here with dilations, and the purpose of this exercise, is to look at these two triangles. One is the dilation of the other. So the pre-image is ABC, the image is A prime, B prime, C prime. So it's been shrunk. What they want you to notice is that the angles stay the same. So angle A is the same as angle A prime, angle B is the same as angle B prime, angle C is the same as angle C prime. And that makes sense because you can't have a triangle be any less than 180 degrees no matter how small you shrink it, right? The degrees don't change. They're a relative measurement. Whereas the side lengths do change. So for example, this guy here, AB is about, let's say 9 centimeters or so. I don't know what it is in your book. And A prime to B prime is 4.5, right? So that would be approximately half the size. A to C is 6 centimeters. So what would you think A prime to C prime is? Well, it turns out it's 3. So most of you just automatically were able to go, oh, the smaller triangle is 1/2 of the length of the big triangle, all the measurements. And that's true. So one of the things I want you to figure out here is that if this is, what did we decide, 4.5 for this one? 5 divided by 9. That's 1/2. So the ratio of these two sides is 1/2, right? The ratio of these two sides is 1/2. The ratio of the other two sides is 1/2. So 1/2 is our scale factor. You can think about it. Sometimes you'll have a positive scale factor where things get bigger, and other times you'll have a negative scale factor where things get smaller, right? Or not negative. Sometimes you'll have I misspoke. You'll have a scale factor greater than 1 where things get bigger, and then you'll have a scale factor less than 1, such as 1/2, where things get smaller. You won't ever have a negative scale factor. My apologies. If you were to draw a dilation, there's a simple trick here, and I'm going to show you because you'll have to do this. O is our center of dilation. We want to draw a ray through O and C. So I just went ahead and put the ruler here as a ray. Then we want to measure the distance between O and C. And in this case, it's 1 inch. We could do it in centimeters too, actually. But I'll do the other ones in centimeters. So this one comes out to 1 inch. So therefore, we multiply it by our scale factor of 3. So O to C prime will be 3 inches. So I'm going to put C prime here. C, it looks like G, but it's a C, C prime. I can do O to A prime as well. So O to A prime here in centimeters, that looks like, probably should have in inches, 1.8 or so. 1.8 times 3 is 5.4, so I'm going to go to 5.4 and put a dot. Oop. And I'll call that dot there A prime. That's an A. And then I'll go ahead and connect these with a segment. It's red, so it stands up better. Okay, and then I can confirm that this works with, let's check O and B. Let's go ahead and put B in here somewhere. So O to B, where's the centimeter side again? Is a little under 1 point, or a little over 1 point. So that's 1.6 centimeters or so. What is 1.6 times 3? 1.6 times 3 is 4.7. 4.7. 8. So go to 4.8, gives me right there. So that's pretty close to that line there. So I'll put B prime. Hooray, I've done a dilation. And we would use this same method if we were dilating a triangle or if we were dilating any other shape. We can simply find our center of dilation and then multiply by the scale factor, however much we want to dilate it by. So speaking of centers of dilation, let me cover those real quick. If I have a shape, and it's most intuitive I found with just a computer-based shape actually, a lot of times when you're like moving windows and computers and stuff, you think about dilations. If I were to change this shape here, so I just grabbed a rectangle, if I hold down shift, so the ratio doesn't change, right? So shift preserves the overall shape of the object. In this case, I'm holding down shift and I can make it bigger and smaller and bigger and smaller, right? So I'm dilating it, but the center of dilation is actually this blue corner right there. It's not actually right here on the shape, it's this blue corner. Notice how I can move this corner still moves if I make it really, really big or really, really small. But it's going bigger or smaller relative to this corner here. So that's another example of a center of dilation. Some properties of dilations: they preserve angle measurements. We talked about that. They preserve betweenness. So basically, if one point is between two other points, it will still be the same after a dilation. Collinearity, same deal. They're all on the same line. If things are oriented a certain way, so if an arrow shape is pointing up, it'll be still pointing up after a dilation. And those are the important ones. So for example, we can check these, and we can figure out whether or not this is a dilation. Does it preserve angle measurement? Yes. Does it preserve betweenness? Yes. Are collinear points still collinear? Yes. Is the orientation the same? No, right? It's been reflected. So no, this is not a dilation. Is this a dilation? Are the angle measurements the same? Well, yes. Is the betweenness the same? There's nothing weird about betweenness or collinearity. Is the orientation the same? Yes. Can we figure out the scale factor? So a couple ways we could do that. One is we could look at, again, the distance between each point and the origin. So from A to the origin, well, not the origin, the center of dilation, which in this case happens to be the origin. So from A to the center of the dilation is 2 units. From A prime to the center of dilation, sorry, not 2 units, over 2, up 2. From A prime to the center of dilation is over 4, up 4, right? So therefore, it's twice the distance of the pre-image, so therefore the scale factor would be 2. Another way to think of that is C to the origin, or the center of dilation, is half the distance of C prime to the same point. A third way you could do it is actually measure the sides. So you could figure out A prime to C prime using the distance formula, and then A to C using the distance formula. And you'll find that A to C is half the value of A prime to C prime. And that one will work regardless of where the center of dilation is. So our scale factor is 2. All right, pause here. See if you can do 5, 6, and 7. They got a little out of order, sorry. So pause. Five, yes, it's a dilation. The scale factor is 3/2. It's getting bigger, but not twice as big. It's 3/2, right? We go from this point here, that's a length of 2, to this length, which is a length of 3. This one asks where the center of dilation is. We can just find it using segments. And then finally, number 6, it is not a dilation, unfortunately, because it's reflected over. Okay, a few other things. We can find where the center of dilation would be simply by lining up our corresponding points and then making rays through them and see where those rays meet. So in this case, we would line up A and A prime and make a ray, C and C prime make a ray, B and B prime make a ray. All those will meet at the center of dilation, which the book usually uses O. And then they made a scale factor from there. So we can do that one, this one here. I'll go ahead and do it real quick. Let's line up A and A prime. Grab Mr. Pen. Cool. I made array. We'll do C and C prime. That's not too bad. And then hopefully that point there will also be collinear with B and B prime. This is our check. That's not bad. Okay. So that point there that they all intersect at is, I'm going to call it out. Measure each point to the intersection O to the nearest millimeter. So go ahead and use your ruler to figure out what those lengths are. The scale factor should be the same. Doesn't matter what type of ruler, whether or not it's off or not. So if it's 8 millimeters from C to O, please use your own values for this, whatever it is. So if this is 8 centimeters, and if it's 4 centimeters from C prime to O, is the scale factor 2 or 1/2? That's the question. Well, are we getting bigger or are we getting smaller? Which one's a preimage, which one's the image? The preimage is ABC, the image is A prime, B prime, C prime, so we're shrinking, we're getting smaller. So our scale factor is less than 1. In this case, our scale factor is 1/2. Then you'll have your own numbers in here. But OC should be twice the value of O prime to C, O to C prime. Okay, see if you can do 8, 9, and 10 real quick. So pause here. Eight asks us to determine the center of dilation and the scale factor of the dilation. Same sort of deal. We can find O as the center of dilation. To find the scale factor, I can do a quick measurement here. I get 7 centimeters for O to A. Sorry, 7, 9. Let's call that 9. And then from O to A prime, I get 3. So therefore, the scale factor is, again, we're shrinking this, so it's going to be 1/3. Oh, it's an ugly 1/3. How is the length of the image of a line segment under a dilation related to the length of its preimage? So let's find out. So we can do a quick check. Let's find the length of AB. So the length of AB is 7 units. The length of A prime to B prime is 2.2, 2.3-ish. I did that. But it's about 1/3, right? It's the same. The difference between those lengths is the same as the scale factor, or the ratio of them, I suppose that'd be a better way to put it. And then finally, what is the result of dilating a figure using a scale factor of 1? It just means it doesn't go anywhere. It's the same thing. It's the same spot. Okay, that's it. That's all I got. Have a good one.